I am Mike Burke, Principal Architect for In-Vehicle Entertainment Systems at Micron Semiconductor. For many years prior to joining Micron, I've been involved in the concept, design, and production of many influential automotive infotainment systems and premium audio systems launched with major automotive brands. Today, I'd like to explore the evolution of automotive cockpits and the important role centralized NVMe PCIe storage plays in the information architecture of emerging vehicles. The automotive industry is going through one of the most significant transformations since the invention of vehicles themselves. Today, vehicle ownership in many cities is increasingly becoming optional rather than mandatory. Manufacturers have adjusted their offerings to appeal to a buyer's lifestyle. Now and in the future, the cockpit experience is central to achieving this goal. Traditionally, brands have differentiated themselves based on powertrain features, styling, and most recently, the in-cabin experience. For the past decade, the in-cabin experience has been defined by the in-vehicle infotainment system. These have evolved from multi-source entertainment, navigation, and personal device integration systems to a fully connected experience. Buyers have been able to create certain levels of personalization based on menu-driven selections, speech recognition, text-to-speech, and more. One of the more recent achievements of the in-vehicle system has been creating a seamless experience for users. Case in point, the integration of Apple and Android devices has become the expectation. As tech-enabled features and functionality in vehicles increase, consumers are increasingly shopping for their new vehicles more like smartphones and tablets, weighing up digital features like personalization, displays, in-vehicle connectivity, and infotainment rather than horsepower, torque, make, model, and design. To keep pace with these evolving expectations, automotive memory and storage, speed of access, and rich data sharing will all become increasingly critical for powering the next generation of connected vehicles. The architecture of IVI systems traditionally have been an isolated one. These systems are based on a closed architecture with features that are hard-coded into the system at the time of manufacture. As such, the overall user experience is based on the state-of-the-art 2 years before a vehicle is launched and is largely static throughout the life of the vehicle. Despite the genuine efforts to offer a compelling user experience, these systems have not been able to keep pace with the level of innovations that consumers expect, which is primarily driven by their smartphone experiences outside of the vehicle. The one key challenge has been the inability to reconfigure and update the system after the vehicle is in the field. That is all starting to change. Tesla set the stage for a fully connected and updatable vehicle user experience. Following suit, Audi recently announced a revised IVI system for its 2021 models. In response to consumers' concerns about sluggish performance compared to their smartphones, Audi now uses a hardware platform that's 10 times faster than its previous generation. The new system also features over-the-air enhancements that can be downloaded throughout the life of the vehicle. This can include an array of personalized streaming content and unlimited Wi-Fi connectivity over a 1 gigabyte per second LTE advanced modem. This is an obvious move to bring the in-car experience closer to what is available from today's consumer electronics. Recognizing changing consumer culture around vehicle usage and ownership, we will soon migrate between owned, shared, and mobility fleet vehicles. The industry has recognized the need for a mobile persona and is now developing a next-generation vehicle cockpit system to accommodate them. There are several fundamental needs of cockpits. They are to identify users, often from a fleet population, onboard and protect their personal preferences, content access, commercial and financial profiles, determine where they sit in the vehicle, deliver an interactive experience to a person individually in a seated location, deliver multiple experiences simultaneously, isolate that user from other passengers in the vehicle where possible, and delete or isolate a user's profile when it's not in the vehicle. We assume vehicles will be part of a mobility fleet. Additional information about the vehicle itself must be stored, maintained, and interact with the centralized mobility service. This includes data about cybersecurity and vehicle security, remote diagnostics, predictive maintenance, vehicle health check, customer connectivity and patterns, navigation, and more. Vehicle manufacturers are currently developing cockpit domain platforms that are intended to provide a level of functionality that maximizes the user experience for all passengers, creates secure personal mobility identity and profiling, enables mobility services within a fleet, and maintains fleet integrity and security while allowing an ongoing refresh of features and functionality over the life of the vehicle. These controllers will utilize multimodal user identification, including speech recognition, facial recognition, biometrics, spatial telemetry for occupant location, multiple instantiations of interactive services such as entertainment, IoT interaction, and more. Profiles for users, vehicle identity and status, local content storage, etc. are creating the need for an overall storage approaching 1 terabyte. The controller will be comprised of several subsystems, including vision systems, multi-source connected entertainment, audio capture systems, an AI accelerator, a connectivity gateway, security infrastructure, and more. With so many subsystems, data ideally needs to be shared between all of these to create a well-integrated solution. Although there is a high volume of data exchange within the system, the user expects the system will behave with minimal latency. As an engineer, we also can't forget system cost. It is paramount to maximize design efficiency as lower cost translates to higher fit rates. From a data infrastructure standpoint, key system requirements include 6 key elements: data transfer speed, the ability to share data between multiple subsystems on one or more compute environments, the ability to isolate processes to ensure design safety and security goals, the ability to encrypt sensitive data where applicable, the ability to securely update and remotely exchange vehicle profiles and stored data, elimination of system redundancies to optimize costs. These attributes, at a minimum, point to a centralized NVMe PCIe storage solution as an advantageous design direction for this architecture. For data storage and access, the PCIe interface offers the highest data transfer speed amongst storage solutions. Automotive-grade solid-state drives, or SSDs, based on the NVMe architecture are well suited to this need, offering data transfer speeds of 3 to 4 gigabytes per second. The PCIe interface protocol is also far more efficient than the other interfaces, offering additional low latency benefits when compared to other storage solutions. An automotive-grade SSD based on NVMe standards utilizes multiple namespace configurations. Namespaces are unique data storage areas that may be privately or publicly accessible. Data that is intended to be shared between processes or subsystems can be defined as public namespace for that purpose. It can also use industry-recognized hardware-based isolation based on single-root I/O virtualization, or SRIOV. This technology allows the system's PCI interface to be subdivided into multiple virtual machines running on the SoC environment that are isolated from one another and each tied to unique virtual functions on the storage device. This technique is well recognized as a secure isolation method. In addition, this technology offers the ability to encrypt sensitive data stored on the drive, such as vehicle firmware, personal identity information, whitelist, blacklist, security profiles, and more. Encryption is protected by symmetric private keys. Aside from encryption capabilities, these devices offer cryptographically protected access control to data regions. These features offer strong benefit not just to the vehicle platform, but to the overall connected infrastructure interacting with the vehicle. Automotive-grade SSDs based on the NVMe standard use cryptographic access control to the overall drive. This feature protects the drive from unauthorized access. Certain keys are used within the system to bind the physical drive to the system architecture and various components to minimize direct security threats. In the past, traditional architectures had a unique individual storage subsystem associated with each function. It should be clear by the benefits described here that none of the system-level benefits would be possible without a centralized storage architecture and a storage solution ideally based on an automotive-grade SSD utilizing PCIe NVMe standards. Centralized storage is necessary to enable data sharing between functional subsystems. It is also fundamental in creating the interactive and personalized user experience that consumers want in their vehicle. An automotive-grade SSD offers a rich set of features including high speed, functional data isolation, cryptographic data protection, secure remote reprovisioning, and much more at a price per density more like isolated storage solutions such as UFS. Aside from eliminating design redundancies, SSDs require little printed circuit area as they are based on small form factor BGA packages. Automotive SSDs with SRIOV features are available in densities ranging from 128 gigabyte to over 1 terabyte and are cost competitive with other storage solutions such as UFS and similar densities. The array of beneficial features of NVMe-based SSDs are available with minimal additional cost. The solution benefits of centralized storage and automotive-grade SSDs discussed here are being applied to next-generation architectures for 2023 and beyond in the areas of not only IVI, but also automated driving and central compute architecture at key OEMs and Tier 1 partners.